Vanakkam, Namaste, Namaskar, and welcome back to Jal Prayag. Today I'm going to continue on the definitions which we have done. We have done two parts of definitions. I'm going to make this a part 3. I'll be dealing with only two definitions, so this video is going to be quite a short one compared to the rest of them. And these two definitions will guide me to the next series of the video also. So let us start off with this definitions, and we'll finish the part 3 of the definitions as well. You can see with the title itself, I mentioned what is the effect of density on draft and displacement, which is very, very commonly used in majority of the stability calculations. So let us quickly go into this. It is in continuation with whatever we did till now. On the part 2, we had finished about 10 definitions. So this is the next of the series. So I'm going to look at the concept, just a quick questions, which will tell me what is it going to lead to the next definition also. So let us see what changes happen to the draft and displacement whenever a vessel which is sailing between two different densities. So what do you expect? Will it change or not change? If it changes, what is the name given to that in stability? So let's continue on that. I'm going to use an example which is commonly used in the basic books also. So I'm considering, let us say, a ship of 10,000 tons. And the scenario I'm going to give is, I'm going to move this vessel from salt water to freshwater. Now, how do you imagine this is a pretty simple. Let me say that I'm just outside the port limits, and I can assume that the water in which I'm floating is salt water. And I'm entering a river port. Although in real life, you cannot have a sudden change between salt water and fresh water. Normally, it is going to gradually change. But for the sake of understanding, I'm giving you a scenario where I'm changing from salt water to fresh water. Let us say this distance also is not too large. So I'm going to show you with a picture. I consider this vessel 10,000 tons. And I'm floating in salt water of 1.025. I've shown you a reference of the Plimsoll mark also. So let us look at this example and continue. I'm going to assume that the distance between just outside the river mouth from where you are coming from salt water and you are entering the river and you are going to a small, let us say, a port or jetty in the river port, and that is having a fresh water. So what I'm going to look at it is, if it is very short distance, with some minor consumptions, I can assume that the displacement is still constant. So I consider the displacement is still approximately 10,000 tons. So it is a good way of understanding, even though it really doesn't happen. There will be a small change because of consumptions. But I'm considering displacement is constant. So this is the principle with which I go. It is also called as constant displacement theory. So I'm going to show you what happens. What do you expect when she enters the fresh water? And I've considered the displacement being still constant of 10,000 tons. So let us say my next journey is towards this water. I'm calling it RD of 1, and same displacement is 10,000. This is what we are going to see, and it will lead to one of the definitions, which is a very important definition used quite a lot. And we'll see what is the link between them to the next video also, which I'm going to make. So this is the condition right now. I have a ship of 10,000 tons just outside the river mouth. I am at seawater. I am entering the freshwater port. What do you expect out of this movement? Now, for you to understand, I'm going to give you the condition. The displacement W seawater is equal to W of the freshwater. This we have already considered. The displacement is constant. I'm going to expand the formula for your displacement, which you know it is underwater volume, into the density in which it is floating. So I marked it green color just to highlight that it is a seawater. Now, if I calculate the underwater volume in this particular example, you can do that in any question. You will see it is coming with this value, 9756.1 meter cubes. Now, again, W saltwater is equal to W freshwater because I consider displacement constant. I'm going to write now what is the displacement formula for freshwater. Again, underwater volume into RD of 1. And this time I'm going to calculate the underwater volume. It comes as 10,000 cubes. Now, it's very evident that the ship which sailed just from saltwater into the freshwater with the same displacement, there is a change in underwater volume. So you can realize the underwater volume in freshwater is more than the underwater volume in seawater for the same displacement. Your underwater volume is directly related to your draft. So very obviously, my draft in freshwater is going to be more for the same constant displacement as you sail from saltwater to freshwater. So I'm going to show you in picture. And this picture gives you a little bit of references. You can see the plimsoll mark has come down more towards the waterline. And I consider that, let us say I had a draft, saltwater draft, whatever was there. And this draft right now is going to be more. So it is evident from the diagram. So this is the concept of a constant displacement vessel moving right from saltwater to freshwater. It is very clear that whenever a vessel moves from saltwater to freshwater, the vessel is going to sink and the draft is going to increase. So I'm going to show you in a picture. If I sail from saltwater to freshwater, I'm going to sink. But the reverse also will hold true. So that means if I sail from freshwater to saltwater, the same vessel, the whole vessel is going to rise and the draft is going to decrease. So in picture, I'm showing you the rise in the direction. Now I've got a very important conclusion here. The conclusion is the change in draft. In both ways, the change in draft is going to be same if nothing else is changing. So this change in draft, when I'm moving the ship only between saltwater and freshwater, is called freshwater allowance. This is the definition which I'm going to see. So let us go more into this freshwater allowance. So freshwater allowance, in other words, can be also mentioned as the rise and sink of the vessel moving in between saltwater and freshwater. So I mentioned this also. This rise and sink is also called as freshwater allowance. Now I'm going to continue with this concept and we'll look into one more definition based on the same thing. Let us look at that. You can realize from the topic itself. Again, freshwater allowance is the rise or sink when moving only in between saltwater and freshwater. So I mentioned here again the same thing because I'm going to build up a new definition now. You should realize that vessel can move in between any other densities. Any other density between saltwater and freshwater is also called as dock water, commonly called as dock water. So I can be moving in between various combinations of densities. It can be just 1.024 also. It can be 1.023 also, 22, 21, and so on. You can go up to this 1. So you can have many number of combinations of densities which you can sail with it. So let us say I have a dock water density. I have not mentioned anything it can be. So I mentioned an intermediate stage, which actually really it happens whenever you sail from saltwater to freshwater. As I told you, the density will not just suddenly change, it gradually changes, and that in between water, what you see is called your dock water. Now I come up with the next definition. This is the second definition which I'm going to talk about. So I can call dock water allowance is the rise or sink of a vessel when she is moving in between any other densities which are not salt water and not fresh water, any other densities. As I told you, various combinations are there. So I'm going to show you here in picture. You can see I've shown you three different diagrams, each gradually from salt water to dock water, then to fresh water. We have already seen direct relation between salt water and fresh water. So now I can show you in picture that this change in draft when I'm sailing from salt water to dock water is also a sink, and it is called dock water allowance. Now from dock water, if I sail to fresh water, that is also called as a sink, and that is also a different dock water allowance, different one. Similarly, if it holds good in one direction, it has to hold good in the reverse direction also. So this is a rise, again a dock water allowance. This is again a rise and again a dock water allowance. So this one picture will very clearly tell you that what is happening when you sail between densities. So you should realize one thing. When I'm moving from a denser water to lighter water, my vessel is going to gradually sink. That means my draft is going to increase. And exactly reverse is when I go from a less denser water to more denser water, I'm going to rise and my draft is going to decrease, provided I keep my displacement constant to understand the concept. Now, this freshwater allowance can be calculated by a simple formula. I'm not going to derive the formula. We'll just see the formula and see what features are there in the formula and how it affects the freshwater allowance. So simple formula is displacement divided by 40 into TPC. The moment you involve TPC, you should realize I've written the units in centimeters. So you need to realize that when you write it, you will come to know, because the numerator has got displacement, which is tons, and the denominator has got tons per centimeter. So both the tons gets cancelled and the centimeter goes up. So final answer is in centimeters. This you should be careful. It's always in centimeters. So W, I can call it present displacement, whatever at whatever draft and displacement you are. And at that particular draft, you will have a TPC, but this TPC should be TPC saltwater, because the definition of freshwater allowance holds good only between two conditions. That means sailing between saltwater and freshwater. You should realize freshwater allowance is directly proportional to displacement, which means that as the draft increases, displacement also increases. So freshwater allowance also should increase because it's directly proportional. Let us look at the denominator. 40 is a constant. I'm not going to talk about it. So let us look at TPC. Your freshwater allowance is inversely proportional to the TPC. But what does TPC depend upon? We have already seen the definition of TPC in the last module. Your TPC depends on water plane area. And you know that as the draft changes, your water plane area also changes. And usually for a ship shape, the water plane area slowly keeps increasing as and when you go. Now, you might say, as the draft increases, displacement also changes. That means it goes up. As the draft increases, the TPC also will go up. So that means the change in displacement and change in TPC may cancel each other. It is not exactly like that. So both W and TPC increase with the draft, but these changes do not cancel each other equally. And you cannot say that freshwater allowance is going to be constant. No, you cannot do that. So what they have found out is for a ship shape, the displacement increases faster than the TPC. Hence, you will see the freshwater allowance also increases with the draft. So you might see in hydrostatic tables a freshwater allowance also given, or you can calculate for that particular displacement with the simple formula. You can always calculate. Okay, now this freshwater allowance is defined only in between saltwater and freshwater. And when we take the values for calculation with the formula, you will see that I'm going to take W and TPC. TPC should be in salt water only. You cannot take any other TPC. So please be careful about it when you're using a freshwater allowance formula. And I've already explained to you that in freshwater allowance, I have a concept called TPC. And when you cancel the units, answer always will be in centimeters. With this formula, answer is always in centimeters. But you should realize that in load line certificates, you may find freshwater allowance mentioned in millimeter also. That is fine. It's converted into millimeters. But this formula, what you see, if I mention as W by 40 TPC, answer is always in centimeters. Now, if you had just seen the load line certificates on board, okay, this is for the people who already sailed. I do agree, BSc boys wouldn't have seen this, but let us say your institute has got some sample or load line certificate. You can always Google also. There'll be a lot of sample load line certificates. You will see that he would have mentioned in the load line certificate only one freshwater allowance. But we saw earlier in the first paragraph itself that freshwater allowance keeps changing with the draft. So that means you should have various freshwater allowance tabulated for you. But then how is a load line certificate only mentioning one? All it is doing is it is giving you for only the summer draft condition or the load displacement condition. So that is what it is giving you. You already know from the definitions, the first series of definitions, load displacement, the definition is locked for a vessel. That means I should be floating in salt water. And at the same time, my plimsoll mark or the summer load line should be matching with the salt water. So it is a fixed locked definition. So that means when he is mentioning freshwater allowance in your load line certificate, he knows what is the load displacement and he knows what is the TPC salt water at that displacement. So he calculates and gives it to you. That is the reason behind giving you only one value. Now, I know freshwater allowance, which is again locked between saltwater and freshwater. Then how do I calculate dock water allowance? You can go by a simple ratio method or interpolation formula. So it is very, very simple, which you have been using in all the hydrostatic tables also. Now, how to relate that? Just let us see. Freshwater allowance is basically the change in draft between two densities, which are freshwater and saltwater. And let us say the units are in centimeters. Similarly, I can find the change in draft between any other water densities. Freshwater allowance was only between freshwater and saltwater, 1 and 1.025. I can calculate the change in draft between any two densities. So let me just put it in the form of a question or in the form of a statement. For a change in density between 1.025 and 1, which is equal to 0.025. You can say the change in draft of freshwater allowance. For a change in density of 0.025, the change in draft of vessel is freshwater allowance. Then what is the change in draft? Let us say for densities between 1.020 and 1.005. I'm just taking an example. It could be anything. So this is the question. The change in density for 0.025 is freshwater allowance. Then what is the change in draft for a density between 1.020 and 1.005? So let us quickly form that equation. I've written the same thing. For change of 0.025, which is the change in density, the change in draft is freshwater allowance. Then for a change of 0.015, that is the change in density which I gave you in the previous slide. I'll just go back to the previous slide. See, I've given you 1.020 and 1.005. So this is the change in density. So what is the change in draft? So all I'm going to do is put an equation. You know that freshwater allowance in this equation is on the right hand side. So I'm going to divide the 0.025. I'm going to send it on the right hand side equation and then multiply 0.015. This is the equation. All I've done is just shuffled it as you would do in any interpolation calculation. Dock water allowance, which is also called the change in draft, is equal to freshwater allowance divided by 0.025, because freshwater allowance and 0.025 are interrelated. That is the change in density and the draft. Multiply with the change in density right now in the question. So whatever answer you get is called as dock water allowance whenever you sailed from 1.020 to 1.005. You can use this formula for any different densities. Answer will come. Whatever units you use in freshwater allowance in this formula, it could be centimeters or millimeters, answer will be exactly the same. Okay. So this is the way I can calculate dock water allowance in between any given. So your questions can come in various, and please use this formula to calculate. A quick question for you. Why in this definition of freshwater allowance and dock water allowance, we are having a word called allowance? So what do you mean by that? Very simple meaning of allowance is something extra. That is what is allowance. So what are we going to do with this extra? And this is what I'm going to look at my next video, which will be the next video within a week or so. You will see a topic called load lines. So I'm going to discuss this allowance and how this freshwater allowance and dock water allowance, everything come into picture based on the load lines. So which I'll be talking in the next presentation, which will be coming soon. So that's the end of this small definitions set of only two of them, dock water allowance and freshwater allowance. I hope this was easy and simple to understand with the figures. And keep watching Jal Prayag. I'm going to come back soon with the next video of load lines. Namaste and Vanakam.